So since we just got done talking about linears and we're moving into quadratics, it's important that we be able to distinguish between the two of them. So we have linear functions and quadratic functions that we're going to learn to differentiate between, and then we have things that are neither linear nor quadratic. There is one other function family we're going to learn, exponential. This is not exponential. Okay, this is actually cubic. That's something that you're going to learn in Algebra 2. But I wanted us to have something that we could see that was clearly not, I mean, I guess so is exponential, but that's neither here nor there. So really what you need to be able to tell the difference is how do I know something's linear and how do I know something's quadratic? So the first way that we can tell is by looking at the shape of the graph. The graph of a linear function, hold on, let me turn this just a little bit. The graph of a linear function is always going to be a straight line. Okay, it's always going to be a straight line. It may be going downhill. Remember, we always sign our line. Maybe negative slope, it may have positive slope, or it may have undefined slope or horizontal slope, but it's going to be a straight line. Now, I'm not even going to go there. Okay, so quadratic has that U-shaped graph that we talked about, which is called a parabola. I know y'all going to be saying parabola just to mess with me, but it's a parabola. Okay, it's a parabola. And that shape, it's a very specific shape. And one of the questions I get a lot is, can it point down? Yes. One of the questions I also get a lot is, can it point sideways? Not if it's quadratic. So no, that function, the quadratic function, does not go sideways. It only goes up or down. Okay? And then if it's anything else, that's an E, then it's neither. And again, there's lots of different function families. You're going to learn a whole bunch of them in Algebra 2. Again, we only focus on 3 of them in Algebra 1, but linear and quadratic is where we're focused on. This one is cubic. There's we will learn exponential. There's inverse variation. There's all kinds of functions. Okay, so that's how we tell by looking at a graph. If it's a straight line, it's linear. If it's a parabola, it's quadratic, and it may be pointing up, it may be pointing down. If it's anything else, it's not what we're looking for right now. Okay, now when I look at a equation, this is going to be kind of, we need to take a little detour here real quick. Okay, just kind of like, we're going to take a step back in time. Okay, so if you recall, I've had this thing that we've kind of written it a bunch of times. We talk about x, and we've been talking about the invisible 1 denominator below it, because when we graph slope, we need to have numbers written as a fraction. Well, so we know it's got an invisible 1 denominator, and we know it's got an invisible 1 coefficient. And I've been telling you that it has an invisible 1 exponent. Well, it does. And that invisible 1 exponent doesn't usually come into play, but when I'm determining function type, it does. So if I look at this function right here, it's got an invisible 1 coefficient and an invisible 1 exponent. And yes, an invisible 1 denominator, but we don't care about that. Okay? And what that tells us is that the highest exponent we see is 1 or invisible. Okay, is 1 or invisible. So we might not, we might see this 1 exponent, we might not see anything. We might just see the invisible exponent. Okay, so it might just look like that. But the highest exponent we're going to see is 1. Okay, question is, could it be less than 1? We're going to talk about that in a minute. Okay. Yes, it could be less than that. There's one other situation that we might see that is also linear. We might see something with an exponent of 0, meaning there is no x. So like y equals x. That's also a linear function. We're not going to talk about that right now. Let's keep it close. Keep it down. Okay. So now when I look at this, I see x squared, which is a 2 exponent. I see my invisible 1 exponent, and I see nothing. I see no letter at all. Well, in this case, because my highest exponent is 2, I'm going to put exp for exponent, is 2, that makes this quadratic. So if the highest exponent is 2, it's a quadratic function. All right. Now, if the highest exponent is not 1 or 2, then it's something else. It's neither. Oops, I don't need if. Sorry, highest exponent is not 1 or 2. Okay, the highest exponent is not 1 or 2. Now, there's one rule that you have to follow in order for this to be linear and quadratic. Okay? So we're going to put a line here that kind of goes all the way across, and we're going to write across these. Your variable can't be in the denominator for these two. It cannot be in the denominator. Okay? If it's in the denominator, you got something else going on. And this is after you simplify it. So let me show you what that looks like. So I'm just going to turn this like this. What if you saw something like this? Y equals 2 over x. Okay, if I put y equals 2 over x in my calculator, let me clear out whatever I got in there. So 2 over x, and I graph it, I get this, which is not linear because it doesn't make a straight line, and it's not quadratic because it doesn't make a parabola. Okay, this is called inverse or indirect variation. Okay, this is not linear and it's not quadratic, but its highest exponent is 1. Well, actually, and we're going to learn all about this in Unit 6, but it's actually its highest exponent isn't 1. When it's on the bottom, when it's in the denominator, it's actually negative. So it's actually 2x to the negative 1. Is that 1 or 2? It is not. And so this would not be, it's not linear or quadratic. Okay? So again, these are kind of the rules. For linear, the highest exponent we see is 1. For quadratic, the highest exponent we see is 2. If it's anything else, if it's anything but 1 or 2, it's neither. And the variable for linear and quadratic, you cannot have your variable in the denominator. Okay, so that's graph and equation. Let's pause for a second now that since we've talked about this, and I want to talk about some vocabulary. So we have 3 terms that I'm going to start using. I need you to know what they mean. We have constant term, linear term, and quadratic term. So we have looked at constant and linear terms. Okay, when we looked at our slope-intercept form here, this is a linear term, and this is a constant term. Okay, well, what makes a constant term a constant term? It is a number alone. Okay, so in this case, like this is a constant term, positive 5, positive 5, positive 4. It could be negative 6 or negative 800. It could be 0. Okay, but the constant term is just a number all by itself. Say a number alone, let's say all by itself. Okay, now a linear term is if there is a linear term, then it's a linear function. If you see the highest you see is a linear term, it's a linear function. So mx, or this is a linear term right here. So a linear term is a term with a variable raised to the first power. So let's actually really quick, let's write some examples here. So like 5, negative 3, 0, 7. Those are all constant terms. So a linear term is a term raised to the first power. Okay, so some examples of that would be like 2x, that's a linear term. Negative 3x, that's a little linear term. For A, B, those are all linear terms because they are terms that are raised to the first power. Okay, let me put a line here. Okay, so up here, negative x would be my linear term. Negative 6x, negative 3x, I'm sorry, nope, no, there is no linear term in this one because I have to the third, to the second, no to the first, and a to the fourth. So there is no linear term in this one. Or you could say 0x. Okay? Now for a quadratic term, I'm looking for a term with a variable raised to the second power. So like x squared, negative b squared, okay, 3a squared, g squared. Let's say, yeah, that's good. Okay, any of these things. So any variable raised to the second power. Now, in this case, we're just talking about terms. Having the highest variable, having the highest, the term with the highest exponent being quadratic, that makes this a quadratic function. Having a term raised to the first power, a linear term as your highest term, makes this a linear function. Okay, so knowing that, again, let's take a pause. I'm going to have you guys check some of these out and make sure you know how to do them. Know what those terms are. Okay, so let's talk about tables. Tables are also just a tiny bit complicated, but it's not that bad. So if you recall, when we talked about linear functions, we had delta x and delta y. Okay, now for these tables, all the delta x's are going to be 1. Okay, so 1 plus 1 plus 1 plus 1 plus 1, and y'all, this is like the carrots. Some of y'all called it carrots because you draw the little carrot, whatever. Okay, now to get from 6 to 5, I subtract 1. 5 to 4, I subtract 1. 4 to 3, I subtract 1. 3 to 2, I subtract 1. Now in this table, every single delta y over delta x is negative 1 over 1, which reduces to negative 1. That is what makes this a linear function, because let's write this. Let's take a minute, and then I'm gonna use a term that may not make sense. So let's write this. The rate of change is constant. Okay, I was gonna say it's the same for all rows, but it's constant. Not to be confused with the constant term. It means the rate of change is constant for every row. That's the cool thing about math. Sometimes we use the same word twice. Okay, so let's look at this one. We have our delta x and our delta y. So these are all plus 1. Will they always be? No, but in this case they are. To get from negative 3 to 0, I add 3. 0 to 5, I add 3. 5 to 12, I add 3. 12 to 21. Wait, what? I'm sorry, math is hard. I don't add 3. Yeah, I do add 3. And then here I add 5, and here I add 7, and here I add 9. Oh yeah, right, that didn't work, did it? I'm sorry, I'm like confused. Like, why doesn't plus 3 plus 3 plus 3 work? It doesn't, because negative 3 plus 3 is 0, 0 plus 5 is 5, 5 plus 7 is 12, 12 plus 9 is 21. So delta y, my rate of change wasn't constant. Delta y over delta x didn't work. So some of you may see right here, though, that if I go out again, 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 2 is 9. Okay, and you notice I wrote down here delta y2. Okay, so for this one, let's see, I can write this. So delta y2 over delta x is constant. And we don't figure out what delta y over 2, okay, delta y2, we call delta y2, we call this the second difference. What do you think we call delta y? Delta y is the first difference, okay? And for a linear function, the first difference is constant. For a quadratic function, the second difference is constant. Okay? So again, let me just highlight this real quick. For a linear, the rate of change is constant. For a quadratic, the second difference is constant. Okay? When we look at a quadratic, so first of all, my delta x's are all going up by 1. Now, let's look at my delta y's. 0 plus 4 is 4. 4 plus 16 is 20. 20 plus 34 is 54. And 54 plus 58 is 112. Y'all don't get it twisted. I already have this written down. See, look, y'all know I take my notes beforehand, but, you know, otherwise. Now, the first difference didn't work. Let's look at delta y2. 4 plus 12 is 16, plus 18 is 34, plus 24 is 58. So the second difference didn't work either. So for this one, if it's anything else, so if delta y1 and delta y2 are not the same. So if delta y over delta, if rate of change is constant, so delta y over delta x is constant, it's linear. If delta y over 2, the second difference over delta x is constant, then it's quadratic. And if it's anything else, it's neither. Okay, you'll try a couple here in a second. All right, so if you have any questions, you know where to type them, or jot them down for me so you can ask me tomorrow. We will practice this.